Another axial flux motor build. Today we're going to look at a design similar to YASA motors, a yokeless stator concept, where instead of a traditional iron core, we're using segmented ferrite pieces with copper windings wrapped around them. This stator sits right between two rotor discs, each carrying 8 permanent magnets. So effectively, we have a dual rotor setup, with the magnetic flux passing axially through the stator. The stator itself has 12 poles, and each pole is wound using two parallel 0.7 millimeter wires with 32 turns per pole. That gives us a phase resistance of roughly 2.5 ohms. This setup is aimed at keeping things compact while still maintaining decent torque and efficiency, especially for a 3D printed prototype. Now, if you're new to axial flux motors, the main difference compared to traditional motors is the direction of the magnetic field. Instead of flowing radially from the center outward, here the magnetic flux flows axially, straight across the motor from one rotor to the other. That's why these are often called pancake motors. And one key advantage here is torque, because most of the force is generated at a larger radius. Now let's focus on the rotor design. Each rotor disc carries 8 permanent magnets, arranged in an alternating north-south pattern. Right now, this is a fairly simple and improvised setup, mainly focused on getting the concept working. In a more refined design, you'd have better magnet retention, improved balancing, and possibly a backing iron to guide the flux more efficiently. But even with this setup, the dual rotor configuration helps concentrate the magnetic field through the stator. One thing with rotors like this is alignment and air gap. Even a small variation in the gap between the rotor and stator can significantly affect performance. And since everything is 3D printed here, maintaining that precision is actually one of the bigger challenges. Also, at higher speeds, magnet retention becomes critical because the centrifugal forces can get pretty serious. But honestly, the rotor is the easier part, where upgrades are limited to steel backplate, trapezoidal-shaped magnets, and Halbach array magnets. That's all that can be improvised in the rotor design. The real complexity in motors like this comes from the stator design. So the stator here uses a yokeless design, meaning there's no continuous iron ring connecting all the poles. Instead, we have individual ferrite segments, each acting as its own magnetic path. Around each of these, we've wound copper coils, 32 turns using dual parallel 0.7 millimeter wire. Using parallel strands helps reduce resistance and improves current handling, but it also makes winding slightly more complex. For this specific motor design, we achieved a very high power density within a compact form factor, delivering 150 watts within a 100 millimeter diameter, including the casing, and a total thickness of just 27 millimeters. The motor is designed to operate on a BLDC style driver at 48 volts and utilizes a concentrated winding configuration. For those unfamiliar with the difference, in concentrated windings, each coil is wrapped around a single stator pole. In contrast, a distributed or serpentine winding travels across multiple slots in a wave-like pattern, typically skipping slots as it progresses. This distinction leads to important performance characteristics. With concentrated windings, only a subset of magnets is engaged during each phase commutation. In our case, only 4 magnets are actively interacting at any given time. On the other hand, a distributed winding configuration engages all 8 magnets during each phase commutation. This results in higher torque density and also offers advantages in terms of achieving tighter and more efficient packaging within the stator core. If we look at this from a magnetic or FEA perspective, the flux from one rotor enters the stator poles, passes through the stator core, and closes through the opposite rotor. Because this is a dual rotor setup, both sides of the stator are actively contributing, which basically means more effective use of the magnetic field. This design is definitely not perfect. The flux path isn't as controlled as industrial designs, the air gap isn't perfectly uniform, and thermal management is still a big question, especially with higher currents. But as a well-calculated and designed prototype, it's a really good way to explore the concept. So let's move on to the interesting part. Let's power this up and see how it performs. All right, that's actually not bad. But let's talk about the limitations. This motor was designed to run at 48 volts, and right now I'm only feeding it 12 volts using a 30 amp BLDC ESC. So the input power is way below what it was designed for. Now this is because I am testing it in my home with limited resources. To properly reach around 150 watts, this setup really needs a lab for testing. So what we're seeing here is just a fraction of its actual potential. The real potential of this design comes with a few key upgrades: a proper steel backplate for the magnets, a segmented ferrite core for the stator, and possibly a serpentine winding configuration. That's something I'll explore in the next version, once I have the resources to push this further. But based on the calculations, a motor of this size, around 100 millimeters in diameter and under 30 millimeters thick, could realistically handle close to 1 kilowatt of power with the right optimizations. And that would be seriously impressive. A high power density motor that literally fits in the palm of your hand. That's exactly what I want to build next. So if this channel gets monetized, I'll be putting that straight back into developing this into a full 1 kilowatt motor. If you want to see that happen, support the channel, share this video, and subscribe. And once we get there, I'll also release a full video breaking down how to actually calculate and design a motor like this from scratch, so anyone curious about the process can follow along and build their own. Finally, if anyone would like to purchase this build model and test it out themselves, the link is provided in the description below, with all the required bill of materials needed. And I'll see you in the next video.